Coastal habitats in Florida often form a habitat gradient that shifts from mangrove forests at the water's edge to salt marshes, salt barrens, transitional high marshes, and finally to upland habitat. The monitoring methods presented here are a part of the Critical Coastal Habitat Assessment, which was developed as a long-term monitoring effort to examine the status and trends of these coastal habitats. Monitoring sites are intended to be revisited every 3 to 5 years to determine how these coastal habitats are responding to climate change, sea level rise, and other anthropogenic impacts. While these methods were originally designed for Tampa Bay, they are broadly applicable to other coastal habitats and locations. This video guide and the accompanying written manual are designed to guide further application for long-term monitoring in the Southeast United States. Site selection. Long-term monitoring sites should be located on protected public or private land that has been designated for conservation in order to guarantee access for long-term sampling. It also needs to be accessible by land or water for elevation surveys and for the scientists conducting the monitoring. Transects should begin at the water's edge and extend perpendicular from the shoreline into upland habitat. Sites should have a moderate slope that transitions through several zones of emergent tidal vegetation to upland vegetation within 100 to 175 meters. Zone boundaries and slope of the topography should be roughly perpendicular to the transect, but there will be natural variation in the zone boundaries. It helps to examine aerial imagery and scout the sites prior to sampling in order to locate areas that meet these criteria. Elevation surveys. Elevation of the transect should be surveyed at a minimum of every 1.5 meters or 5 feet. These elevation surveys can be conducted using an RTK GPS or by traditional land surveys. Because you will be surveying the vegetation along the transects, avoid clearing away vegetation from the survey paths as much as possible and avoid trampling one side of the transect. Because the substrate is often soft in wetlands, it's recommended to use a wide diameter base on the surveying equipment to prevent them from sinking in the sediment. Elevation benchmarks. Establish semi-permanent elevation benchmarks at the beginning and end of each transect. Benchmarks can be constructed from rebar, which is then capped or covered by a PVC pipe. Benchmarks should ideally be hammered to a depth of refusal, but that's not always practical in deep sediments. In addition to the transect, elevation should also be surveyed at the top and bottom of each benchmark.
Habitat transition. Extend a transect tape along the surveyed transect and identify locations of habitat transition. Habitat transitions may be identified by shifts in plant species or locations with significant elevation changes. Note that not all shifts in vegetation may be accompanied by a pronounced change in elevation, but should still be considered separate zones for monitoring. Install a physical marker such as a PVC marker or wooden stake at each transition and record the latitude and longitude. These marked locations will also provide a visual aid while extending the transect tape on return trips to the site. Assign each zone a letter and a name and record the width of each zone. Include at least 10 meters of upland habitat at the end of the transect, as this region may shift to high marsh vegetation in future years. Transect vegetation. Record plant cover along the transect in half-meter increments to document gradual shifts in vegetation. Starting at the water's edge, place a 0.5 by 0.5 meter quadrat with one edge along the transect. A cube design minimizes the need to bend over, while removing one side of the cube allows the structure to be placed around trees. Record the basal percent cover for each plant species within each quadrat. Note, basal cover records the amount of cover where the plant grows out of the ground and is significantly lower than total percent cover. In addition to all plant species, also record basal percent cover by pneumatophores, woody debris, and macroalgae. All remaining area within the plot is assumed to be bare or detritus. This category includes both bare sediment and leaf litter. Identify each plant species if possible. Upland grasses may be identified by genus if it is impractical to identify species. Take a photo of the vegetation every 5 plots, 2.5 meters along the transect, and record the photo file number. Randomized plot establishment. A stratified random sampling design is used to capture information within each vegetation zone. Randomly select 3 plots per zone within 10 meters of the transect. Randomized plots can be selected in the field or using a GIS platform. In the field, a random number generator can be used to generate a random distance along the transect, followed by a distance from the transect within the 20-meter wide belt. Alternatively, after zonation has been identified in the field, a 20-meter wide grid may be created in a GIS platform. 3 randomized grid cells can then be identified within each zone. Randomized plots should be marked with a PVC pipe and additional flagging tape as necessary, and the latitude and longitude should be recorded to mark the location. While creating the randomized plots, keep in mind that the zone boundaries are often not fully perpendicular to the transect. If a randomized plot is intended for Zone A, yet actually falls within the vegetation characteristics of Zone B, create another randomized location so that the randomized plot falls within the vegetative zone of interest. Also note that each transition zone should include a randomized plot, as these locations are more likely to capture vegetation shifts on 3 to 5 year timescales. Randomized plot vegetation. Record data on basal percent cover of plant species within the quadrat. Like the transect, this percent cover should include pneumatophores, woody debris, macroalgae, and in mangroves, red mangrove prop roots.
For the basal percent cover, you're going to record all of the plant species that are present in the plot. For the mangroves, because the red mangroves have prop roots that hit the ground, we are counting where the prop roots hit the ground as part of the basal percent cover. So we'll add that together with the red mangrove cover of the trees as well. For the pneumatophores, we're recording percent cover of the pneumatophores, but we're not differentiating between black mangrove and white mangrove pneumatophore. It all gets lumped together in one mangrove category. Woody debris we count as a separate category, but leafy debris and bare ground, we're assuming that the remainder of the plot that's not covered by plant, that's going to be within the leafy debris and bare cover category. So your total should sum up to 100%.
Record canopy cover directly over the PVC marker using a canopy densitometer and/or spherical densiometer. Randomized plot fauna. Record the number of littorina snails and fiddler crab burrows in each quadrat. Photograph and identify species present in the zone, including area outside the plot, as crabs will likely flee upon approach. In mangroves, record the number and species of tree crabs present within each quadrat. Point-centered quarter sampling. From the PVC marking the center of each randomized quadrat, record data for point-centered quarter PCQ sampling. PCQ sampling is a plotless method designed to capture information on tree density within a forest. The region around the PVC marker is divided into 4 imaginary quarters. For CCHA methods, align the quarters to be parallel to the direction of the main transect. Measure the distance from the PVC to the base of the nearest tree in each quarter. The base should be measured where the trunk intersects with the ground. Trees may be located inside or outside the 1 by 1 meter quadrat. Record the tree species, diameter at breast height, which is 1.3 meters above the ground surface, and tree height for each of the 4 trees. A tree must be greater than 1.3 meters in height in order to measure a DBH. Tree diameter may be measured using tree calipers or a diameter tape, while tree height may be measured using a surveying rod or clinometer. PCQ sampling may be omitted if you would need to sample beyond the current vegetative zone in order to locate a tree of sufficient height. For instance, PCQ sampling is not needed in salt marsh zones that lack tall trees. See references in the accompanying manual for instructions on how to calculate forest characteristics from PCQ data.
Measuring tree height. For all of the trees that you measure for PCQ sampling, we're also going to record the tree height. So you can use a survey rod to record tree height. If you don't have a survey rod, we can determine it using a clinometer. So for that, we need to measure the distance from the person taking the measurement to the base of the tree. There are various types of clinometers available that we can use to measure that visual angle to the top of the tree. To determine the height of the tree with a clinometer, you can purchase clinometers. So with this one, I need to input the distance that I'm standing from the base of the tree, and then I'll input the angle, the visual angle to the base of the tree, and then to the top of the tree, and the clinometer will calculate the tree height from that data. If you don't want to purchase a clinometer, you can also make your own. So this one is made using a protractor and a straw taped on top with a nut on a piece of string. You can use this to measure the visual angle to the top of the tree. So with the visual angle, the distance to the base of the tree, and the eye height of the person taking the measurement, you can then calculate the height of the tree.
Feldspar. Feldspar marker horizons provide a method of measuring sediment accretion on top of a substrate. A 1/4 inch thick layer of white feldspar clay is applied to the surface of the marsh in a marked location. Subsequent coring in this location allows for the visual examination of the thickness of sediment deposition on top of this layer. Place feldspar marker horizons at one randomized plot per vegetation zone near the center of the zone. Just outside of the 1 by 1 meter plot used to survey vegetation, place a 0.5 by 0.5 meter wooden square in a flat location that has received minimal trampling. This location should have similar elevation as the center of the randomized plot, as the elevation of this location was surveyed during elevation surveys. Mark 2 to 4 corners of the feldspar square by hammering 4-foot sections of steel rebar into the ground, then cover the rebar with a 1/2 inch PVC sleeve. Remove any large pieces of woody debris from the square and sprinkle the feldspar in a layer at least 1/4 inch thick. Feldspar may be sprinkled on top of and around existing vegetation. Use a concrete trowel to flatten the feldspar into the sediment. Wear a mask to avoid inhaling the feldspar. Feldspar plots should be cored every 6 to 12 months in order to gauge sediment deposition using a coring device with minimal compaction, such as a Russian-style peat corer. Cryogenic coring devices also have minimal compaction. In this method, liquid nitrogen or dry ice is used to freeze the sediment before the core is drawn up out of the ground. Record the amount of soil deposition as the average of 4 measurements from the top of the feldspar layer to the surface of soil. Make note of the location where coring occurred, then replace the sediment core. Avoid coring in repeat locations and at locations with visible bioturbation.
Porewater and soil sampling. Sample pore water and soil adjacent to the same randomized plots that were used for feldspar marker horizons. Dig a hole with an auger until you reach the water table. If sediment is relatively dry, you may need to let water percolate into the hole for half an hour before you collect pore water. To improve comparability across locations, pore water sampling should be conducted near low tide for all plots and sites. Record time and date of pore water collection to facilitate tide and precipitation comparisons. Measure the depth from the surface of the sediment to the pore water. Use a pipette or hand pump to collect the pore water. A handheld salinity refractometer is recommended for determining salinity, as only a few drops of pore water are required for measurement. Label a plastic bag that will be used for a soil sample with the site and plot information. Remove leaf debris and use a trowel to remove a sample including the top 5 centimeters of soil for grain size and organic content analysis. Use a ruler or knife to separate the top 5 centimeters of soil and place it in a bag. This soil sample should be refrigerated upon return from the field. Lab analysis. The amount of organic matter in the sediment can be determined through elemental analysis or through loss on ignition methodology, which is what will be shown here. The sediment sample from the top 5 centimeters that was collected in the field should be refrigerated after collection. Homogenize this sample by mixing the soil in the bag and place it in a weigh boat. Take a subsample of the homogenized sample and place it in a pre-weighed crucible. Save the remainder of the sediment sample for grain size analysis. Record the wet weight of the sample in the crucible. Dry the sediment at 105 degrees Celsius for 24 hours, and then record the dry weight of the sample and crucible. The sediment is then combusted at 550 degrees Celsius for 3 hours and weighed again in order to determine weight loss due to combustion of organic matter. If you wish to determine the amount of inorganic carbon in the soil, you can combust the sample again at 950 degrees Celsius for 1 hour. The additional amount of weight lost is due to combustion of carbonates in the soil. The ramp time and cooling time needed for the furnace to achieve these temperatures will vary by manufacturer. Equations for the calculation of organic matter, organic carbon, and inorganic carbon can be found in the manual accompanying these videos. Grain size can be determined through several methods, including laser diffraction, X-ray attenuation, and scanning electron microscopy. However, you can also use more low-tech methods, such as settling tubes and sieves. Here we're going to use sieves of various mesh sizes in order to separate sediment into multiple size fractions. Put the remainder of the surface sediment sample in a weigh boat and dry the sediment at 105 degrees Celsius for 1 to 4 days before putting it in the sieves. Record the weight of the sediments throughout the drying process. The sample is dry when it retains a constant weight and is therefore no longer losing water to evaporation. Place the sample in a stack of pre-weighed sieves that are ordered by mesh size. This will separate out the sediment into various grain sizes. After shaking the sieves for 3 minutes, manually or with an electric sieve shaker, remove one of the center sieves and record the weight. Then replace the sieve in the stack and continue shaking for an additional minute. Weigh the same sieve again and repeat the process until the weight remains stable and the sample has completed separation. You can determine the weight of each size fraction by measuring the final weight of each of their pre-weighed sieves, or if you're using a sensitive scale, place each sediment sample in a pre-weighed weigh boat, being careful to remove all sediment from the mesh of each sieve. Data analysis. GPS data should be compiled and uploaded into spatial software, such as ArcGIS or Google Earth. Create a map of the transect, complete with labeled lengths of each of the vegetation zones. Use statistical software to calculate average basal percent cover within each zone, and calculate basal area of trees from PCQ data. Predictions of sea level rise can be compared to elevation graphs to obtain a visual estimation of where sea level will fall along the transect. However, this method does not take rates of accretion into account.
Future sampling. Return to sites within 1 year to core at Feldspar locations to determine rates of accretion. Repeat vegetation, Porewater, and soil analyses every 3 to 5 years. The accretion rates provided by Feldspar data can be compared to local rates of sea level rise to evaluate if wetlands may be able to maintain their current positions in the intertidal zone. Coastal vegetation at many sites will likely be forced inland. Information on rates of landward migration of vegetation enables prioritization of specific habitats for conservation, restoration, or protection of adjacent upland areas. Results from ongoing CCHA monitoring at sites in Tampa Bay are available from the Tampa Bay Estuary Program's technical website. Implementation of these monitoring protocols across a wider geographic area in coastal wetlands of the southeastern United States will allow for comprehensive regional comparisons of wetland response to climate change and sea level rise. We hope you have found this video training manual to be informative. Please consult the accompanying printed manual or the Tampa Bay Estuary Program with further questions.